system set up and talking about an algorithm for figuring out the coefficients. The idea behind that, again, was that we first looked at the linear splines and said, well, linear spline is just plain connect the dots. You get all those sharp corners probably when you hit each of the dots. So we want to try to smooth things out. But when we smooth it out with the derivatives, we don't necessarily make the curvature match. So what we're going to talk about today is extending this idea to cubic splines and making the curvatures match. And you can imagine that why you want to try to make these things as smooth as possible is if you're trying to build something that needs to be hydrodynamic or aerodynamic, you don't want it to catch on things that are not very smooth, right? It causes all sorts of different things. Maybe if you're thinking about building an aircraft, if it's not perfectly smooth in a certain way, it might make turbulence and make the airplane shake, which would be a bad thing. I know that from experience over the weekend. On Thursday, I had a really, really bad landing in Dallas. In fact, had to abort the landing the first time. That was frightening. Not as frightening as coming in the second time, and the plane went like this. I mean, it was pretty scary. But okay now. I mean, I was better off than some other people that needed a little bags in the seat bag. So it was quite fun that day. But I made it, I suppose. So not a lot you can do at that point. You're on the plane. So anyway. But again, like I said, you can imagine that if you're trying to build these things and making them bend, you want to make them bend as smoothly as possible because you don't want to catch weird things like that, right? Or if you've got something going through water, you don't want to create whirlpools around little things, right? You want to make sure you're going through the water or through the air or what have you as smooth as possible. So that's the idea behind the cubic splines, that when we're going to get to these interior knots, those interior points, we're not only going to make the function values and the first derivatives match, but we're also going to make the second derivatives match. Okay? So the idea here is that I'm going to make the formulas a little bit different than what they do in the text. I think it's a little bit cleaner, a little bit nicer, and then we'll talk about hopefully how we can get these things put into Excel and then R. Pardon me. So let's say again we have the knots. In this case, I'm going to start with a 1. So let's say we have n knots, and I just blew right over the top of my dots. So our points here are y1, x1, y1, x2, y2, all the way up to x sub n, y sub n. Pardon me. So again, the idea here is that we want to make sure that we have functions that take on these values at the individual points, but we also want to make sure that we match up at the endpoints correctly. So whatever I'm using for the first polynomial, my first cubic, the output here, the y2, needs to match the output at x2 for the second cubic, and so on up the line, just like we did for the quadratics, right? All right, so to write this in a little bit simpler form, let's say we're going to use the functions s sub I. It's going to be a cubic function, so that means we're going to have a constant term, an x term, an x squared term, and an x cubed term, right? But let's make it so that it makes it a little bit easier for evaluation, at least to make our equations match up nicely, and we've done this before. So whatever the constant happens to be, but let's, pardon me, instead of doing powers of x, let's do powers of x minus x sub I for each of these. So we'll have b times x minus x sub I, or b sub I times x minus x sub I, c sub I times x minus x sub I squared, and d sub I times x minus x sub I cubed. The reason why we want to write it this way is hopefully it's pretty obvious what the a sub i's have to be pretty quickly. Right? Because when I put x sub I into s sub I should be getting that left endpoint, right? So what is the a sub I going to have to be? the y sub I, right? Okay. So if we write it that way, it makes it a lot easier to figure out what the constant is, right? So there's not a lot of work. So in fact, instead of writing it as an A, I'm going to change it to a y immediately. Okay. So when we write it in that form, in powers of x minus x sub I know what the constant term is. So really, I need to worry about what the coefficient on the x term is, the coefficient on the x squared term, the coefficient on the x cubed term. Okay. So we've got n minus 1 polynomials defined, right? Each of those has 3 coefficients. So I've got 3n minus 3 coefficients defined, which means I better create 3n minus 3 equations at the end, right? I need as many equations as I have unknown so I can solve for all of the coefficients exactly, right? Now remember when we did the quadratic splines, we did the similar counting idea, but there was a coefficient that we didn't know, so we had to make an assumption about the first one, right? We're going to have something similar happen here for quadratic splines. All right, so again, the idea here is we're going to make our equations from making sure the endpoints match, making sure the derivatives at the endpoints match, and making sure the second derivatives at the endpoints match. That's how we're going to get our sets of equations here, right? So when we put in I plus 1 for I, or x sub I plus 1 in for the function, for the ith function, I better get the same thing as when I plug it into the I plus first function, right? You agree with that? This is what's saying when I get to the right end point of the ith polynomial, I have to have the same function value as when I'm at the left end point of the I plus first polynomial, right? So, pardon me, this is going to give you, pardon me, n minus 1 equations, because I've got n minus 1 polynomials to start with, right? I think this gives us n minus 1 equations. Pardon me, goodness. In any event, we'll count them at the end to make sure that we'll see what we have wrong at the end. How many we are short, not necessarily wrong. We also need the same thing to happen at each of the interior points, right? So I need first derivatives to match at those points. So this says that the first derivative at the right end point of the ith polynomial has to equal the first derivative at the left end point of the I plus first polynomial. Right? So that's making the slopes match. These are similar to what we had for the quadratic ones, right? Right. Now notice that these are all in the interior, so I'm not using the first term here, and I'm not using the last one, right? I'm not using this last endpoint. I'm not using the first endpoint. I'm using the ones in the middle. So instead of getting n minus 1 equations there, I'm getting n minus 2 equations. So I'm missing one, right? This one gives me n minus 1 equations, but this one gives me n minus 2, right? You agree? Okay. The same thing will be true with the second derivatives. Again, I'm not worrying about what's happening at the leftmost endpoint and the rightmost endpoint. So again, this only gives me n minus 2 equations. If I add n minus 1 plus n minus 2 plus n minus 2, I get 3n minus 5 equations. And we said we needed 3n minus 3 equations, so we're too short, right? Because I had 3n minus 3 coefficients I needed to do, so I'm too short. So when you do cubic splines, you have to have information. You have to have information that allows you to figure out each of these equations exactly. So you've got to make some assumptions of what happens, and usually you're making those assumptions of what happens at the left endpoint and the right endpoint. Remember, with the quadratic splines, we said one of the things that we could assume was that the curvature on the first spline was 0. It was just really a linear function to start with. All right. So we can do the exact same thing with the cubic splines. So one thing that you might do is what's referred to as a natural cubic spline. When you hear the word natural cubic spline, this says that we're going to assume that the curvature at the leftmost endpoint is 0, and the curvature at the rightmost endpoint is 0. So this is one way to handle the missing information, making the curvature at the very, very left point and the very, very right point 0. There's another one that's referred to as a clamped spline, a clamped cubic spline. From clamped, we set these values equal to something specific rather than being 0. We'll talk about clamped ones later. We're going to do this for a natural cubic spline today. But we understand why we had to put extra conditions in here to get enough equations, right? This works, this gives you n minus 1 equations, because I'm going to start here, but I'm going to go all the way across. These two, I don't get enough equations. Okay. All right. I guess I should say the last equation, of course, is because when I hit here, I have to hit the last endpoint. That's where I'm getting that extra equation here versus these two. This one actually takes into account the last point. All right, so let's talk about how we're going to solve these things. So there's a good deal of algebra that we'll do, but the goal here is to we're going to write this in a certain form so that we'll be able to solve the system easily rather than have to go through a big, long-winded, if you've done one your algebra, row reduction or something along those lines, right? Because again, you've got a lot of coefficients to solve for, and we want an algorithmic method to do this. Okay. All right. So let's use these pieces to help us out to get equations to solve. All right. The idea behind this, by the way, is we're going to use the first and the last set of conditions to plug in to the middle one here and figure out the coefficients in the middle. So we're going to actually figure out the C's. And once we figure out the C's, we can get the B's and the D's. All right, so that's how we're going to head this off. All right, so let's look at the first two equations to start with. This one again says that if you put I plus 1 into the x sub I plus 1 of the ith polynomial, you have to get the same thing as when you plug in the x sub I plus 1 into the I plus 1 polynomial, I plus first polynomial. Okay. Well, the right-hand side of this is easy, right? Because when I plug in the left endpoint of the I plus first polynomial, I have to get the y sub I plus 1, right? Because if I replace all the i's with I plus 1s and then plug in x sub I plus 1, it kills off those last three terms, right? So this one, from this equation, one side of your equation is just going to be y sub I plus 1. The other side will be y sub I, and then plus b sub I times x sub I plus 1 minus x sub I, c sub I times x sub I plus 1 minus x sub I squared, and d sub I times x sub I plus 1 minus x sub I cubed. That's one set of equations, right? Now, there's a lot of notation in here. So let's try to see if we can simplify things a little bit. Notice what we have in parentheses here is a change in x. And I'm not going to do it right this second, we will in a little bit. If I were to subtract the y sub I over to the left-hand side, I would also have a change in y. Greek letter we use for change in is delta. So I'm going to use a little delta to represent this change and a big delta to represent this change. Okay? So to help us write this a little bit nicer on the right-hand side, actually what I'm going to do, I'm going to go ahead and just subtract this over I want to write this as y sub I plus 1 minus y sub I. I'm going to call that capital delta sub I for the left-hand side. Then on the right-hand side, we'll have y sub I plus b sub I, delta sub I, c sub I, little delta sub I squared, d sub I, little delta sub I cubed. This is just to simplify the notation for us. Okay. Yes? Oh, yep. What y sub I? I don't see a y sub I, do you? Of course, I'm recording, so later on you can just say, well, let's watch the tape. All right. Thank you. Bless you. All right. So, again, this is just the first equation. The first set of equations gives us this condition for the d, the c, and the d. Okay. Let's use the last one here, the second derivative. When we take the second derivative, what happens? When we take the second derivative, this goes away, certainly. But so does this one, right? Okay. So when we do the second derivative, I just have those two pieces. So when you do your second derivatives, I'll write down what the derivative is, and then we'll get the equation. So your s sub I double prime of x will be 2c sub I plus 6d sub I x minus x sub I. Right, when I take the second derivative, you bring down the 2, you'll have a 1 left, and then you'll bring down the 1, and then you do the 0 power, so it just goes away. And the second time the second term will have, excuse me, not the second term, I guess that's the fourth term. We'll bring down the 3, then to bring down the 2, there's still a first power left, and we take the second derivative. Yes?
Check for taking the derivative with respect to
X. Yes, yep. That's okay? All right. So this is true for any I. So again, this third condition here that we have says that when I plug in the right endpoint for the second derivative of the ith polynomial, I get the same thing if I plug in the left endpoint for the I plus first polynomial, right? Well, when I plug in x sub I plus 1 into the I plus first polynomial, this one goes away, correct? So we're left with 2c sub I plus 1 on... That's all that's left in that one, right? Because it'll go away. This one will make this one go away. When we put in x sub I plus 1 here into the ith polynomial, you'll get 2c sub I plus 6d sub I delta sub I. Yeah, lady.
Can you explain how you got the 2c sub I plus 1?
Sure. So when I'm doing the I plus first polynomial, that replaces all these with I plus 1s all the way across. Then when I plug in x sub I plus 1, this condition here, that term completely goes away. When I change this I to an I plus 1 and then plug in I plus 1, x sub I plus 1 for x. So that completely goes away. So that's all that's left. Yeah. I'm doing a kind of flip-flop. I'm doing the right-hand side of the equation on the left-hand side down here. I can now solve this for d sub I. Your d sub I here will be, well, I would subtract the 2c sub I over and then divide by 6 delta sub I. So I'll get c sub I plus 1 minus c sub I over 3 delta sub I. So much like what we talked about with pardon me, the quadratic splines that we did last week. If I know the C's, I can figure out the D's. Remember when we did the quadratic splines, we had A, B, and C to figure out. We worked with the B's, which I think are both called Z's, which it doesn't matter. If I knew the B's, I could figure out the C's, and then we concentrated on figuring out the B's, right? So it's the same idea here. If I know the C's, I can figure out the D's. So our goal is going to hopefully be able to figure out the C's here. Okay? All right. Now, we've got D in terms of C. I've got D in terms of C. I've got this equation now that relates, this one here, sorry, I'm going to the wrong one. This one here that relates B, C, and D in the delta, but we know the delta. I'm going to plug in the C sub I minus, what this expression is here for the D sub I up here, and get my B sub I in terms of the C's. Okay? So we're going to use this, what we just found, substitute it up here, and solve for B. So we'll get the B's in terms of the C's. So again, once we figure out the C's, we can figure out the other coefficients. That's the goal. Okay? All right, so we plug that in. So again, I'm going to take this and plug it in right here. Okay? So we get delta sub I equals B sub I little delta sub I, C sub I little delta sub I squared, and then C sub I plus 1 minus C sub I over 3 delta sub I times delta sub I cubed. Again, I want to find the B in terms of the C's. So I'm going to move everything over and divide by delta sub I. Okay. Okay. So what happens when we do that? So let's see, this delta sub I here, I'll get rid of that one. So I'll get a delta sub I squared, right? I'm going to divide, let's see, let's just rewrite this a little bit. This is what? I'm going to just play with this for a second. This is C sub I plus 1 over 3 delta sub I and a minus C sub I over 3 delta sub I, all right? Delta squared, sorry. All right? That's just this piece here. Notice I've got a plus C sub I delta sub I squared here. So I'll have 2/3 there. You agree with that? Okay. So if I solve this for B sub I, then I'll have delta sub I over little delta sub I. Because I got to divide this delta sub I out. We'll have minus 2 C sub I over 3 delta sub I and a minus C sub I plus 1 over 3 delta sub I. Right? I could make that look a little bit prettier because I could factor out a minus 1/3 here. This is what's equal to your B sub I. You could factor out a minus 1/3 here and leave it as 2 C sub, you might factor out a minus 1/3 delta sub I, and then you have 2 C sub I plus C sub I plus 1. Yeah. So if you wanted to write it that way. We would have that for our B sub I. You can see why you would never want to do this by hand, by the way. Lots of numbers, lots of things to keep track of. That's our goal here, is just to try to get this set up so that we can just change numbers or put something into a program, right? We don't want to have to do this by hand every single time. This is also why your only assessment on cubic splines is going to be your major assessment. So I'm not going to have you do this in class. That's not even worth the time and effort to try to memorize it all and then regurgitate it out with a calculator. Okay. All right. So again, this is much like what we did for quadratic splines. We've just done it with a little bit more information, right? Remember with quadratic splines, we worked with the C's in terms of the B's and then figured out what the B's had to be, right? Okay. Same concept here. We've got the B's and the D's in terms of the C's. So we got to figure out a way to figure out what the C's are. Okay? That's our goal. Now, we used the second derivatives to get this piece of information for the D's, right? We used the original function to get this piece of information for the B's. The only thing we haven't used is the derivatives, right? So we need to work with the derivatives set equal to each other in order to get the equations to solve. All right, so let me scroll back up for a second. Here was our relationship that we need to use to get those equations set up. Right? Okay. Pardon me. When we do that in this case, your S sub I derivative will be, well, the A sub I will go away. You'll be left with B sub I plus 2C sub I x minus x sub I and a 3D sub I x minus x sub I squared. Everybody agree with that? What the derivative is going to be? Okay. So again, we're going to use that condition. I'm going to write down the condition again so we can see what the equation needs to be. The condition that we need is that when we plug in the right endpoint to the ith derivative, we need to get the same thing as if we plug in the left endpoint into the I plus first derivative. Say it again. What's a zero?
On the left side, x of something.
That's I plus 1. That's the right endpoint. It's just an I plus 1. It was just my pen dragged. It made a mark. What is the right-hand side of that equation equal to? It's b sub I plus 1, right? If I replace all of the i's here with I plus 1s, and then plug in x sub I plus 1, these two terms go away, right? So we're just left with b sub I plus 1. On the right-hand side, the right-hand side of this equation, which will be the left-hand side of this one, we'll get b sub I plus what? Good, little delta sub I and good. 3D sub I delta sub I squared, exactly, yep. Now notice that these are just for the interiors, right? So this will work for your with the I equal to 1, because we're not doing this at the with I equal to 2, we're not doing this at the first endpoint, up to I equal to n minus 1, right? So this will be equations that we'll use for the C sub 2 up to the C sub n minus 1, okay? All right. All right. So let's start plugging some things in here so that we can get equations now, right? I've got an expression for the B's in terms of the C's, and we have an expression for the D's in terms of the C's, right? Okay. So let me work from right to left, actually. D sub I again, let me scroll back up. This was our expression for the D sub I here, right? So we'll get C sub I plus 1 minus C sub I over 3 little delta sub I times little delta sub I squared there. Yeah. B sub I plus 1, here's the expression for our B sub i's but I need to replace the I with I plus 1, right? So we'll get, on the left-hand side, capital delta sub I plus 1, little delta sub I plus 1, minus little delta sub I plus 1 over 3 times 2c sub I plus 1 plus c sub I plus 2. And I didn't leave myself nearly enough room. No, I do.
Great. That really helps me.
Helps you out, doesn't it? That's the nice thing about taking notes there, writing on here. I didn't have to erase anything or put a little caret or something. All right. The exact same expression that we have on the left-hand side here is going to go in this gap here, except now I want my with an I rather than an I plus 1 everywhere, right? So we'll have exactly what we have written up here. We'll have delta sub I over little delta sub I minus delta sub I over 3 times 2c sub I plus c sub I plus 1. Bless you. Good news is we're going to go through all of this, and we'll never go through it all again. We're going to set things up. I just want to show you where everything's coming from. What's algebra for? I like algebra so it's not even hard algebra. This is all high school algebra, just lots of letters. Are we okay up to here what we have? Now again, the whole idea here is that we're going to set up a system of equations. Okay? So we have a whole bunch of unknowns. We have n unknowns here, right? I've got C1 up to Cn unknowns. This gives me currently n minus 2 equations, because again, it does not give me an equation for the first C, the C1, because that's at the left endpoint. It does not give me the equation for the last C either. We'll handle those separately, okay? But let's see if we can get this into some form that doesn't look so gross, relatively speaking, okay? By collecting like terms. So remember, if you're trying to solve a system of equations, if you've taken linear, you know that you want to get all your variables on one side and your constants on the other. If you have taken or are taking linear, right? But generally speaking, when you're trying to solve a system of equations to start with, maybe you're trying to solve a couple of linear equations. Maybe you have 2x plus 3y equals 9 and 6x minus 4y equals 11, something like this. If you have something like this, usually you want the variables on one side, constants on the other, because you're trying to go through a process of eliminating a variable, right? Okay. So usually we try to get all the variables on one side and all the constants on the other. So looking at this particular equation, here are my variables with the C's. These are the only constants we have, right? Okay. So we're going to move this constant to the other, this constant, and move it over here, and then take this thing with the variables and move it over here. Okay. So to do that, I'll just subtract the capital delta I over little delta I over to the left-hand side. Let's see what we have on the right-hand side. Well, we would add this to the other side, correct? Yeah? Okay. So when we add this to the other side, that was interesting. It made a little arrow. I didn't draw that arrow. I couldn't draw that arrow that nicely if I tried. That was weird. We're going to move that to the other side. That was pretty fun. All right, so let me distribute that through as well. We've got a delta I plus 1 over 3. Well, I'll write it as 2 delta I plus 1 over 3. C sub I plus 1 plus delta I plus 1 over 3. C sub I plus 2. And then the other stuff I'll distribute as well. 2 delta I over 3 C sub I. Oops, that's a minus. Delta I over 3 C sub I plus 1. 2 C sub I delta sub I. In the last term, notice that the delta sub I in the denominator will cancel and the 3's will cancel. Right? So we're left with a plus C sub I plus 1 delta sub I and a minus C sub I delta sub I. I know, lots of letters. We're getting there eventually. Okay, so let's collect things that have the same, let's collect like terms. Let's work with, I've got a C sub I, I've got a C sub I plus 1 and a C sub I plus 2. I'm going to write this in increasing order as we go, for lack of any other better order to do it. I've got a plus 2C sub I. I've got minus a C sub I. I'm not worried about the deltas because they all have a delta attached to them, right? Okay. Here's a C sub I with a delta sub I. Here's a C sub I with a delta sub I. Here's a C sub I with a delta sub I. 2 minus 1 is 1. Minus 2/3 gives me a third, right? So we've got delta I over 3 C sub I. That's it for those. I'm going to just cross those off so I don't work with them again. Okay? You can cross them off or not in your notes. I'm just crossing them off so I don't look at them again. Okay? Let's do your C sub I plus 1s. Here's a C sub I plus 1. Here's a C sub I plus 1. Here's a C sub I plus 1. This one, this first one has a delta I plus 1 in it, right? The other two have delta sub i's. But notice that this is 2/3 delta I plus 1. When I simplify this one and this one, I'll also get a plus 2/3 delta sub I, right? So I can rewrite this as 2/3 times delta I plus 1 C sub I plus 1. Yeah. That's where this one is.
Oh, sorry.
Yeah. Yeah. That's because this one has a delta sub I plus 1 on it. Right? It's this one and this one I can actually combine, and then we'll put that one with it. All right. Took care of that one. This is the only one that has a C sub I plus 2 on it. Oops. So we have a C sub I plus 2 here. And that's still equal to your left-hand side that we had before. Say it again? Oh, it's delta I plus 1. Yes, thank you. Thank you. I can make this look a little bit nicer even if I multiply both sides by 3 because it gets rid of those fractions on the right-hand side. So we get these equations. Delta sub I C sub I plus 2 times delta sub I plus 1 C sub I plus 1 plus delta sub I plus 1 C sub I plus 2 equals 3 times what was on the left-hand side. Now again, this works for this is the equation we come up with for I equals 2, I equals 3, I equals 4, all the way up to I equals n minus 2. Right? Because those were the interior points that we did, right? From 2 to n minus 2. Okay? So for the 1 and the n minus 1, we're going to go back to the fact that we're doing a natural cubic spline. So remember, a natural cubic spline says the curvature at the endpoints has to be 0, right? So when you do the first one, so when we did your the second derivative at the first endpoint needs to be 0, right? What we had. Now remember, your second derivative looks like 2c sub I plus 6d sub I x minus x sub I, right? Oops, I wrote d sub I and I mean a 1. We're doing the first function, right? So our derivative was 2c sub I plus 6d sub I times x minus x sub I. My I is 1, correct? Yeah, I is 1. Yeah. With I is 1, then this piece here goes away. That's 0. So what does c sub 1 have to be at the very end here? Yeah, so this tells me that c sub 1 has to be 0 to start with, okay? So that's one equation, okay? I'm going to keep track of that equation, by the way. So, but anyway, c1 has to be 0. The last one says that when I do the n minus first polynomial, second derivative of it, and plug in the right endpoint, I also have to get 0. Right? That's what the last one says. So this would tell me, give me one more equation. I would have, I need that line. Oh, it doesn't matter. We would have 2c sub n minus 1 plus 6 6d sub n minus 1 times x sub n minus x sub n minus 1. Right? Agree with that? Okay. So what this does is it's going to tell us what the actual last one has to be as well for the last polynomial. Because again, remember we're doing 1 to n, right? Or 1 to n minus 1, I should say. Sorry. So anyway, look at this last coefficient that we'll have. There is a c sub n that's implied in here. Remember, our d sub n minus 1 would be c sub n minus c sub n minus 1 over 3 delta sub n minus 1. I know we didn't actually write a c sub n in there for any of the polynomials, but notice this last one, we're going to use this to help us with an equation, by the way. This last one here, notice that when you simplify, the 6, the 3 will make a 2, right? Your delta sub n minus 1s will cancel. So you'll get a minus 2c sub n minus 1 and a plus 2c sub n minus 1, so those go away. So what does c sub n have to be? 0, right? That c sub n helps us solve these equations, by the way. But this last one also tells us that c sub n has to be 0. Remember that this equation that we came up with here should work if we have n minus 2 in for I, right? We went from 1 to n minus 2. When I put n minus 2 in here, I get a c sub n. So I need to be able to figure out what that one is. Okay. This last condition tells us that the c sub n actually has to be 0. Okay. All right. Phew, that's a lot. Okay. But what this does now is it actually gives us a system of equations now since I've introduced this extra variable of c sub n, it gives me n equations with n unknowns. There's n minus 2 equations here, one here, and one here. So again, if you write this in matrix form, remember if you write a system in matrix form, we think about the columns being what the variables are. Oops. And then these would be your variables here. And then your constants would be over here. Oops, I need a little extra room here for the constants. All right. The very, very first equation for C1 was that C1 was equal to 0, right? So I'd have 1, 0, 0, 0, dot, 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 0 equals 0 up here. Right? We agree with that? Okay. The very, very last equation was C sub n equals 0. So you'd have 0, 0, 0, 0, dot, 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 1 equals 0. Right? And then the other ones actually have some meat to them. So just to remember that the equation looked like I can remember what it looked like. That, didn't it? All right. Okay. So, pardon me, goodness. So the first thing we should get here in this equation is what? So the first equation would have delta 1 2 times delta 1 plus delta 2, and then plus a delta 2 times that one, right? So we should have delta 1 here, 2 times delta 1 plus delta 2 here, and delta 2 here. And then the rest of the rows should be what? Zeros, yeah. When we do the next equation, instead of plugging in a 1 for I, we'll plug in a, and I haven't filled in the constant yet, but that's okay. We'll do that in a second. When I plug in 2 for I, I've got C2, C3, C4 for my variables, right? So what does my row look like there? Yeah, a 0 here. This one's going to be delta 2, right? This one will be delta 3, and this one will be delta 3, and the rest will be zeros, right? And then here would be 0, 0. We'd have a delta 3, 2, delta 3 plus delta 4, and I didn't put a column there, but it'd be delta 4, right? And keep going. We agree with that? Right before the last one here, I would have a delta n. If we put in n minus 2 for I would have an n minus 1 here for this one. This one would be, the previous one would be 2 times delta n minus 2 plus delta n minus 1. And then we'd have a delta n minus 2 here. That would be the one right before the very, very last row. Now your constants here are going to be your, this would be 2. Like so, all the way to, oops, this one. There. Whew. Notice the form of your system here, and we're going to make it a little bit nicer, in fact, because we want to try to get to the point where we're going to solve the system that we want to solve, right? We want to find the coefficients for the spline so that we actually have these cubic splines found for us so that we can piece pieces together. All right. Are we okay with how I set up the matrix here? Okay. All right, so let's look at what we need now if you were to solve this. Now, of course, you know what the C1 and the CEN are equal to, correct? So there's not a lot of computation you have to do there. However, if you remember stuff from doing elimination ideas, remember even when I go back to this simple idea, if you wanted to solve this equation here, I could multiply the first one by -3 and add down and get rid of that, right? We can use that exact same idea for bigger systems. So I could do -delta1 times this equation and add it to this equation, right? And make this a 0. Make that go away. Notice it doesn't change anything else in that entire row, right? Because everything else is zeros. Right? Nothing else changed. Okay? So that basically eliminates this. I don't need to worry about this row or this column anymore. I can get rid of that. Right? Over here at the bottom, I can do the exact same thing. I can do -delta(n-1) times this one and add to that one and make this go away without changing anything else in that entire row. Right? So really what we need to solve is the following. So we need to solve the system that looks like 2 times delta1 plus delta2, 0. Then the next one was, what was here? Delta2, 2 times delta2 plus delta3, and a bunch of zeros. All right. The next one would be 0, delta3, 2 times delta3 plus delta4, and a bunch of zeros, right? I'll write one more just so we can see what it looks like. To there, right? The same pattern would continue. What happens at the very, very end here? Well, your I did put a bunch of zeros here. I'm going to put a couple of an extra 0 here. Your very, very last row at the end will have a delta(n-2), this piece here, and a 2 times delta(n-2) plus delta(n-1). That would be your last one. Notice we've got this thing going diagonally down to the right. Right? You agree with that? Okay. As we have this thing going diagonally down to the right, and notice there's basically 3 diagonals here, right? We actually refer to this as a tri-diagonal system. You've got the main diagonal here going from upper left to lower right, and then you've got the one above and the one below as we're going along. So that would be your matrix on the left-hand side. I would have C2, C3 to Cn-1 here, right? And then I would still have my constants on the right-hand side. The 3 delta2 over little delta2 minus delta1 over little delta1. Same thing for the next one. That was weird. To there. All right. So this is the system that we need to solve, which looks kind of gross, but it's not too bad. Because we can either program it, or we can put it in Excel and let Excel do it. So let's see how we would do it if we're thinking about programming it or putting it in Excel. So rather than doing this with letters all over the place, let's say we had a specific example with some numbers and how we would do it, and see then if we could come up with formulas for what we would need. Okay? So, because when you would have all these values already computed, correct? Remember, the deltas are all your distances between the x's, right? This is your difference between x1 and x2. This is your difference between x2 and x3, x2, 3 and x4, and so on up the line, correct? So you just have numbers that you would need here, right? So let's see if we had something very specific to try to solve, see if we can figure out what the algorithm would be, and then get some things figured out for either Excel or R or whatever programming package you want to use. So to make this look like something we might do, just make up some numbers here. 4, 7, and then, oops, I'm going to do an augmented matrix. I'm just making up numbers as I go along here, by the way.
So delta 4 does not have to be the same as delta 4 here as well.
Oh, it does. I'm just trying. I was want to try to come up with an algorithm to solve it. Yeah, you're right. Those numbers would have to match. You're exactly right. I'm just making up numbers so that we can come up with an algorithm. Is all. Okay. I just figured it was easier to do with numbers than a bunch of letters. We agree this looks like a tri-diagonal system? All right. So let's see if we can come up with a method for figuring out what these values would have to be. Well, it would be nice if at the very, very end here I had a 0, right? That would be nice, wouldn't it? At the very, very end here I had a 0. Well, if I had a 0 here, because I could then read off the solution here, couldn't I? Because this is just telling me the last variable would have to equal whatever number is here, right? Well, to get rid of this one, I need to use something up here, but notice I already have a constant here. So I need to go all the way back up to here, make this a 0. When I make this a 0, I can work off of here to make this a 0, work off of here to make this a 0, work off of here to make this a 0. Okay. So notice we're going to step to the right when we do that. Now, ordinarily, when you think about taking a linear algebra class, you try to make this a 1 and then get a 0, right? Well, from the computational standpoint, I don't really need to make it a 1 to start with, right? I could just make sure I make this a 0, right? So to make that 8 a 0, I could do what? Yeah, so it'd be -2 times that first row and add it to the second row, right? Where did the -2 come from? Yeah, that's the 8 here divided by that 4. Right? You agree with that? So notice when you do the 8, so I already have this number stored here. I wouldn't have to change it, right? This number, I know how to get rid of this one by doing -8/4, right? And add it down. Well, if I do it here, I have to do it here as well, don't I? Right? So this new one here, this 3, would get replaced with 3 plus 7 times -8/4, right? That's what it's going to get replaced with. I'm trying to think of an algorithm to do this, right? That's why I'm not changing the numbers to start with. I'm trying to think of an algorithm to do it, right? Do we see why I would do -8/4, by the way? Right? I'm trying to make this a 0 here, this 8 a 0. So I have to figure out what to multiply this by so that when I add down, it makes that go away. Yeah. That's what that new number is going to be. I'm trying to think about it from an algorithm standpoint, from a programming standpoint, right? Now, I don't need to keep track of this anymore because it's going to go away, right? And notice that when you do this, it doesn't change this number either, does it? So I don't have to worry about changing that one. Okay? But I do need to change this one. Now, once I've changed it, whatever this becomes here, what is it, negative 11? Doesn't matter what it is. Once I've changed it, now I'm going to work off of this one to get to that one to make that a 0, right? We agree? And then do the same thing here. You change that number there, right? That'll become what your new one to work off of. Work down, and this will change that number there, and keep going down until you get to here, right? Okay. So let's see if we can do it a little bit more algorithmically, like I'm mentioning here. So if you've got, let me try to make it a little bit smaller. This is delta 1. Sorry, I got the wrong number. Well, it doesn't matter. Those are the notes that you had to start with, right? So if you've got this list of numbers to start with and you want to figure out how to replace this list of numbers here, what would you multiply by to go down here? Right, and then that's what you would multiply this by to get rid of that, make that a 0, right? So this term right here, you would take this times another delta 2 and add it to your 2 times delta 2 plus delta 3, correct? Whatever's stored in there, right? And keep working down that way, right? All right. So let's see if we can figure out what this might look in Excel, because I think we could do this in an Excel way. Hopefully. Let's start with a smaller system here so they're not going crazy with all this stuff. Trying to pull one out of a book here. So let's see. Certainly we gotta have something with some points in here. I'll just make it up, it doesn't matter. Let's say we have, let me zoom in here. Let's say your points are, let's say your X's are 1, 3, 6, and 9. And then your Y's are, let's say, -2, 4, 1, and 8. Okay. All right. So the things that we're going to need are what in our system? So let me write the system back down again. The system looks like we start with a delta, a 2 times delta 1 plus delta 2 and a delta 2, right? And then we have a delta 2, a 2 times delta 2 plus delta 3, and a delta 3, and so on down the line, right? In particular, I need to know what those deltas are, right? Okay. So let me just label that here, just so that I know what I'm computing, so that we can refer back to them. So remember, your deltas are just the difference between consecutive x's, correct? Okay. So this one would be your C2 minus your C1, or B2, sorry. And then I should be able to just oops, that's the wrong thing. I did the y's. Sorry. I'm going to need that too. I need my x's. I need C1 minus B1 here. With 4 points, I only have 3 deltas, right? All right. That's the left-hand side. Remember, your right-hand side also has those deltas in there as well. Those, correct? Okay. So we need to calculate those capital deltas as well. Now I'll get the right numbers. I put those in there so that we can hopefully fill this out pretty quickly. Okay. All right. Now, again, we've got a tri-diagonal system, and when we write the matrix down, we think about it in a diagonal fashion, but we're only working off of certain terms in the previous rows, right? So I might as well just make everything vertical. There's nothing that says I have to make everything exactly what it is, right? All right. So notice in this case, we've got 3 deltas here, right? So we're going to have 3 rows when we're done. Okay. So I'll just make it over here. I'll make the 3 rows, but I'm not going to make it going down diagonal. I'm just going to make it vertical with what the rows are going to be, right? I'm going to write my first row, then my second row, then my third row. Okay. Just make them, well, in this case, I guess it would look exactly like that anyway. But your first one's going to be what? 2 times your first little, looks like I hit equals in there. 2 times the sum of the 2 deltas, right? Your delta 1 plus your delta 2, right? You agree with that? Okay. Actually, I think I'm going to move that out, and I'm going to leave it here for right now. We might change it on Thursday, but I'm going to leave it right there for right now. All right, so we're trying to get this set up so that all you're going to do is copy and paste down if you've got bigger systems. So the way I have that right now, I think I actually want to move it over a column, but that's okay. The way I have it. You know what? I lied. I'm just going to move it over now. Oops. There we go. This one's going to be your delta 2, which is this one. So that was 2 times delta 1 plus delta 2 and then delta 2. Right? Okay. So over here, this is going to be your, I'm going to make them vertical. So I'm going to think about moving everything just to make it into a big vertical line, right? That's my thought, is just to make everything in a big vertical line. So this one's going to be my delta 2, which will be this one. Oops. Equals that one. Okay. This one will be 2 times delta 2 plus delta 3. And then this one will be your delta 3. Yep. How did I get C7? Yeah, it should just be the delta 2 here. Yep. I think I might have deleted this one. I think I should have made a bigger system. Because I think this is all the equations we have. Because we only have 3 polynomials that we're trying to find. So I think I only needed the 2 equations. So I think I should have made a bigger system. Anyway, well, let's come back to this on Thursday. So that we can get it actually put in here, because I only have 2 minutes anyway. Okay. We'll make a slightly bigger system so we can see how this is set up. But the idea here is, remember that we're going to use, even though this is now in a vertical line, I would use this number to get rid of this value. Right? And then store, and then we'll have to use that one as our next one. So we should be able to put a set of values on the right-hand side to keep track of those things for us as we go along. So we should just be able to have another set of 3 values going down over here to help us out as we go. Right? So we'll do that on Thursday. But again, on Thursday, the first thing I want to do is get all your programs integrated so that we can simply see that all work. Okay? So that's a big thing for Thursday. All right? All right. Have a good one. We'll see you on Thursday, if not before.
Like today, I can